So guys, we are going to continue discussion with respect to statistics, and in this topic we are going to discuss about something called as covariance. Okay, a very super important topic in statistics, covariance. So we'll try to understand why do we specifically use covariance, what is the formula of covariance, and after this we also have topics like Pearson correlation coefficient, Spearman rank correlation coefficient. So first of all, let me just give you a very good example. Okay, in machine learning, whenever you are specifically working with data sets, right? Suppose if I consider that I have a data set which have features like X and Y. Okay, suppose these two features are basically there now, or let me just consider, let me name this feature in a better way. Suppose I have age, I have weight, right? Suppose these two features I have in my data set, and probably I will write some data over here. So suppose I say for 20 age, the person was 75 kg. For 18, the person was 63. For 15, the person was somewhere around 45. For 14, the person was somewhere around 40. Another age I may take for 25, the person was somewhere around 78. Okay. So age over here is basically the unit of measurement is years, and weight, the unit of measurement is kgs. Okay. Now, when I have this two specific feature, okay, when I have two specific feature, now let me just name this as X and let us name this as Y. One relation that you can basically see that as the age keep on increasing, right? As the age keep on increasing, the Y value is also increasing. This is one amazing property that we can get from here. Let's see one example. When the person was 14 years, he had an age of he had weight of 40 kg. Then when the person was 15 years, 45, 18, 63, 20, 75, 25, 78. So as the x is increasing, y is also increasing. Whenever you have this kind of properties, so you can also find out one relationship that when the x is decreasing, y is also decreasing, right? And you may also have some kind of data set when probably your x value is increasing, y may be decreasing, or when your x value is decreasing, y may be increasing. So this kind of property you may also have, right, within your features. Now, if I really want to quantify this kind of properties in some numerical relationship, at that point of time, I can definitely use covariance. So I'll just write it down over here, why I will specifically use covariance. So here I am basically saying that a very important point, I want to quantify, oh my God. Okay, quantify the relationship between x and y. Okay, so between the features I really want to quantify or provide some kind of relationship. Okay, so that is the reason why I will specifically use this kind of covariance concept. Okay, and remember, when I say quantifying the relationship, I'm basically applying a formula where I get some kind of numerical values through which I can definitely say whether it is positively correlated. Positively correlated basically means when x is increasing, y is increasing, when x is decreasing, y is decreasing. Negative correlation basically means uh, when x is increasing, y is decreasing, when x is decreasing, y is increasing, right? So some kind of relationship with some positive numbers or a negative number. Okay, so for this I will definitely use covariance. Now let me go ahead and define the covariance formula. And remember, I will show you a lot of examples with respect to this. So if I really want to define the covariance between x and y, my formula will be something like summation of I is equal to, and two more things in this. Okay, so covariance can be defined from population also, for sample also. So the first formula that I will probably define is for population. If you have a population data, probably how covariance formula will look like. So I will write covariance of x comma y, summation of I is equal to 1 to capital N, okay, where N is the size of the population. Then I have x minus x bar. This x bar is the mean of x. Mean of x basically means mean of the x feature. Then I have y minus y bar divided by capital N. So this is the formula of covariance. Uh, In order to find out the covariance between x and y in a population data, I will basically be using this. Similarly, in the case of sample, okay, sample, if I really want to write covariance of x comma y, here I can basically write summation of I is equal to 1 to small n x minus x bar divided by y minus y bar divided by small n minus 1. Now, why small n minus 1? Because we have learnt about the concept called as Basel's correction, right? And one more term that we can basically use is degree of freedom. So degree of freedom is nothing but n minus 1 in the case of sample. Okay, so just remember this. In the previous session I have already discussed. Now over here, you know, x bar is the mean of x, y bar is the mean of y, capital N is the population data, sample you have n minus 1. Now let's go ahead and let's try to solve a problem. Let's consider two real world examples, probably where we can definitely apply in finance data also. So I have a feature which is called as, suppose let's consider that I have a feature which is called as economic growth in percentage. Okay. So I have an economic growth in percentage, and let's consider my another feature which is Nifty 50 index. Nifty 50 index is nothing but it basically has a portfolio of 50 stocks, well performing stocks, and people can directly apply for this particular portfolio, and based on that they can also get a lot of growth and returns. Okay. So we are trying to find out, suppose in my data set I have these two features, that is economic growth in percentage and Nifty 50 index probably also in percentage. So this can be my x the x data, this can be my y data. Now I really want to find out any relationship is there or not. First of all, let me write out the data. So 2.1, 2.5, 4.0, 3.6. So this is my data set. Okay, and then here I have values like 8, 12, 14, 10. This basically shows that when the economic growth was 2.1, my Nifty 50 index grew by 8%. When the country's economic growth was 2.5%, the Nifty 50 index grew by 12%. Similarly, this was when the economic growth of the country was 4.0%. At that time, Nifty 50 index increased by 14%. Okay. Similarly, you have all these values. Now, let's consider what is x over here and what is y. Okay, so what I'm going to basically do is that again I'm going to create some table, because I really want to find out now the covariance, right? I really want to find out the covariance between x and y to see whether it is moving in a positive way, or whether it will have a positive covariance or a negative covariance. That we are going to basically see. Okay, now let me create the table. Right now, for this particular value, economic growth, I'm going to mention it by x. So x, I already have 2.1, 2.5, 4.0, 3.6. Okay, and then y, I actually have 8, 12, 14, 10. Okay, so this is the two columns that I specifically have. Now what I am actually going to do is that I'm going to basically find out the covariance, right? Covariance between x and y, and obviously I know the formula of covariance of x and y. Let me consider that I have my population data. Yes, you can also do it with sample data, because I'll divide by n minus 1. So this is nothing but x minus x bar summation of I is equal to 1 to capital N y minus y bar divided by capital N. Okay, so the first thing that I really want to find out is x bar. What is x bar? What is this x bar? This is the mean of x, right? So what I am actually going to do, if I really want to calculate the x bar, I just will take the average of 2.1, 2.5, 2.4.0, 3.6. And for this, if you go ahead and calculate it, which is pretty much simple, I will get 3.1. Just try to do it. Okay, mean of x, I think you should not have any problem, because now we are in the advanced stage. Instead of wasting time, so I'm going to directly write the value with respect to the calculation, but you do it. Okay, similarly this y bar, if I really want to find out, again summation of all these particular values are divided by 4, right? The total number of values. So here I'm actually getting 11. Okay, 11. Now if I go with respect to this particular formula, the first thing that I really want to find out is x minus x bar. Okay, so x minus x bar is nothing but 2.1 minus 3.1, which is minus 1, 2.5 minus 3.1, which is minus 0.6, and then I have 4.0 minus 3.1, that is 0.9, and then I have 3.6 minus 3.1, which is nothing but 0.5. Very simple. And the next column that I am going to calculate is y minus y bar, because this is the next thing that I really want to find out. So 8 minus 11, I am going to do, I'm going to get minus 3. 12 minus 11, I'm going to get minus, 1. 14 minus 11, 3. 10 minus 11, minus 1. So I've got all the values that is basically required over here. Now let's go and apply and see what is the relationship between x and y, whether it is a positive number, whether it is a negative number. Okay. If it is a positive number, then two properties will get satisfied. If it is a positive number, these two properties will get satisfied, but that is when x is increasing, y is increasing. When x is decreasing, y is decreasing. Okay. If it is a negative number, then I can definitely say when x is decreasing, y is decreasing. Sorry, when x is increasing, y is decreasing. And when x is decreasing, y is increasing. So these two properties will get satisfied with respect to positive or negative number of the covariance. Now I have all the values. Now what I'm going to do, I'm going to find out covariance of x comma y. First of all, summation of I is equal to 1 to n, right? So what I'm going to do, first of all, let's go ahead with finding this with respect to the first record, right? This first record. Okay. So obviously you know the formula, x minus x bar multiplied by y minus y bar. Okay. So the first thing first, what is x? X of I minus x bar, this is nothing but minus 1 multiplied by minus 3 plus, then you have 0.6 multiplied by 1 plus 0.9 multiplied by 3 plus 0.5 multiplied by minus 1, right? Divided by the entire n. N is nothing but 4, right? So here what I'm going to do, in this particular case, I'm going to just consider this as my sample. Okay. So I will just drop this. So this will be small n and this will be small n minus 1, right? Because I have the sample data. You can also do with capital N, not a big deal. So here I'm going to basically say 4 minus 1. Perfect. Now do the calculation. 3 minus 0.6 plus 2.7 plus 0.5 divided by 3. Okay. So here if you try to go ahead and calculate it, it is nothing but 4.6 divided by 3, which is nothing but 1.533. Okay. This is your answer of the covariance of x comma y, where x is your economic growth and this is your Nifty 50 index. Okay. So since this is a positive value, two things that you can take out from this, that is, let's consider this. That is, if you're considering this, that basically means that you are probably satisfying two conditions. You are satisfying two conditions. The first condition is that when economic growth increases, right? When economic growth increases, your what is increasing? Your Nifty 50 index growth is increasing. Growth is increasing. Okay, perfect. So this is the first condition. The second condition that you are probably going to consider is that when the economic growth is decreasing, then Nifty 50 index growth is decreasing. Okay, so these are the two things that you can definitely come up with. Just imagine if you had a negative value, then what would have happened? Then you would have satisfied this condition where x is increasing, y is decreasing, and when x is decreasing, y is increasing. So this was a perfect example with respect to covariance, where I have actually taken an example. Now, one thing that you have to note over here, whenever you try to find out covariance of x comma y, it is possible that you'll also get a negative value if this condition is getting satisfied. Okay. But one thing that you'll note that there is no restriction of any positive value that may be coming or negative value that may be coming. It is unlimited. You may also get plus, in some of the example, you may also get plus 1000. In some of the example, you may also get minus 1000. Okay. So there is definitely no restriction at all. Okay. You can have any value that you want. You can have definitely any value that you want. And that is non-stoppable, right? But it is always a good criteria that we should restrict these values. Otherwise, it will be very, very much difficult to compare between between a set of data sets with the other data set, right? So in order to prevent this, what we do is that we basically use something called as Pearson correlation coefficient. So that is where, in order to not restrict it, suppose I want to just restrict it in some way between -1 to +1, right? I want to provide some restriction. That basically indicates that if I go more towards +1, I may say that yes, it is more positively correlated. If I go more towards -1, it is that much negatively correlated. Okay, but in this case, whether you get any value, any positive value or any negative value, you will not be able to still compare that how strongly it is positively correlated or how strongly it is negatively correlated. Okay, so for this case, we will try to use the negative correlation, sorry, the Pearson correlation coefficient, which I will be discussing after this. So guys, let's go ahead and discuss about Pearson correlation coefficient. We are going to take the same example that we have probably taken in the covariance example. So here, economic growth and Nifty 50 index growth, right? So I'm going to take that same example, and just before just starting to implement or try to find out the Pearson correlation coefficient, what I'm going to do is that let's plot some kind of charts. So suppose this is my this two graphs. So suppose this is my economic growth, okay, and probably this is my Nifty 50 index growth. If you see some of the points over here, guys, let's see. I'm going to make it as 2, 4, 6, 8, 10 in the economic growth, and probably I may start from 8, 10, 12, 14, right? And most of the points, the first point is somewhere near 2.1 and 8. Okay, so I am going to basically plot over here, and then probably 2.5 and 12, I'm going to plot it over here. Then I have 4 and 10, 4 and 14, sorry. So I'm going to plot it over here, and 3.6. 3.6 is somewhere here, and I'm going to basically plot at 10. Okay, so it will be somewhere here. Okay, now what do you see over here? Obviously, you can see that when x is increasing, y is increasing. If x is decreasing, y is decreasing, right? One thing I told about covariance is that when you are trying to find out the covariance, you are either getting a positive value or a negative value. But how strongly positively it is correlated, how strongly negative correlated it is very much difficult to say. Because if I say that, okay, through covariance you are getting plus 100, and probably or by using the covariance you are getting minus 50, definitely this value is not restricted. We are able to get any value. So in order to overcome this disadvantage, we basically use Pearson correlation coefficient. Okay, now Pearson correlation coefficient, let's see how it is basically implemented. First of all, we'll discuss about the formula. Pearson is basically given by this symbol, that is Pearson correlation coefficient of x comma y, is nothing but the formula is very, very simple. That is covariance of x of y divided by standard deviation of x multiplied by standard deviation of y. We have already calculated this, guys. See, in our previous example that we have seen, 1.533 I have got, right? So this we have already calculated it. Now we really need to go ahead and try to calculate the standard deviation of x and standard deviation of y. Now obviously, if you really want to calculate the standard deviation of x, the formula is quite simple. Okay, so here I am going to take as summation of I is equal to small n x minus x bar whole square divided by small n minus 1. So this is the formula that we basically use for standard deviation. Now let's go and see x and x bar. So already I have x and x bar written over here, right? For you, x and x bar, right? I have very much easily written 2.1, 3.1. We have done this kind of calculation. So I am just going to expand this, okay? So probably you can just check out all those things what I have actually discussed. So the first thing that I am going to basically write, let's go above, and I have written it in my book also for the calculation so that I don't have to go above. So it will be 2.1 minus 3.1 whole square plus 2.5 minus 3.1 whole square plus 4.0 minus 3.1 whole square, then 3 plus 3.6 minus 3.1 whole square. So this is what I am actually going to write. So it is very much simple. So let me just write it down over here. So the first instance, if I try to subtract 2.1 minus 3.1, it is nothing but minus 1 whole square, right? Then the second one is basically 0.6 whole square. Okay, I think minus 0.6 whole square. Then the third one is nothing but 1.1 whole square. Okay, 1.1 whole square. And then I have 0.5 whole square. Okay, so you can definitely check that out. N minus 1 is nothing but the total number of elements are 4, so I'm going to basically write it as 3. Okay, so here again let's verify whether it is right or not. 2.1 minus 3.1 is 1 minus 1 whole square. I've written 2.5 minus 3.1 is 0.6 minus 0.6 whole square. 4.0 3.1 is nothing but it is nothing but let's see, 4.0 minus 3.1, it is nothing but, I'll just make a change, small change over here. Okay, it is nothing but 0.9 whole square. 0.9 whole square. Okay, mistakes happens, it's fine. If probably mistake is coming, you try to fix by yourself, right? 3.6 minus 3.1 whole square is nothing but 0.5 whole square. Now we will go ahead and calculate it. 1 plus 0.36 plus 0.81. Okay, 9 nines are 8. 0.81 plus 0.25 divided by 3. Okay, so I will just open my calculator over here. 1 plus 0.36 plus 0.81 plus 0.25 divided by 3. Obviously, I am getting somewhere around 0.806, right? So I'm getting 0.806 with respect to standard deviation of x. Now, similarly, I will go ahead and calculate the standard deviation of y. So formula will be simple. I is equal to 1 to small n root of y minus y bar whole square divided by n minus 1. Now, one thing I missed out over here, guys, I used root of, right? So in order to find out root of 0.806, okay, so I'm just going to use this. Probably I have a root of 0.806 is nothing but 0.8981. Okay, square root of this is nothing but 0.89. I hope so I'm right. Let's see. So 0.8981. Okay, now the same thing I'm going to do for, first we'll calculate this internal one and then we'll do the square root. So y minus y bar for the first instance, what it is, 8 minus 11 is 3. So 3, then 1, then 3, then 1. Okay, so it's very much simple. So I'm going to write it as minus 3 whole square, okay, plus 1 whole square plus 3 whole square plus minus 1 whole square divided by 3, right? So I have 9 plus 1 plus 9 plus 1, which is nothing but 20 by 3, which is nothing but 6.66. Now I need to find out root of 6.66. Okay, so I'll open the calculator. Let's see, root of 6.66. Did I get the value? No. So 6.66 root is nothing but 2.58. 2.58. Okay, let's see this also. So I don't know whether I did it right. 0.806 root is 0.8977. Sorry. Okay, so 0.8981. Okay, perfect. We are getting this perfectly. Two values. Yes, we have got it. I have already known the covariance of x comma y. Now I'm going to divide it by 0.8981. 0.8981 multiplied by the standard deviation of y, which is nothing but 2.58. So that's it. Okay, now let's go ahead and do the calculation. So if I go ahead and do the calculation, this is 1.533 multiplied, no, divided by, first of all, let me multiply this, 0.8981 multiplied by 2.58. So I'm getting 2.317. Okay, 1.53 1.533 divided by, again I forgot it, I don't know what it is, 0.8981 multiplied by 2.58. So here is my denominator. I'm going to write it down. 1.533 divided by 2.317. 2.317. Now, finally, if I calculate it, so it is 1.533 divided by 2.317. Perfect. So I've got around 0.66. Okay. So this basically means, and always remember with respect to correlation coefficient, your value, one very important point, always your answer will be ranging between -1 to +1. Now you may be thinking why? Because we are finally dividing it by standard deviation of x and standard deviation of y. So we are always going to get all the values between -1 to +1. This indicates that it has a positive correlation and it is strong. 66% it is positively correlated. Okay, so I hope you have got this idea. Now let me just show you one Wikipedia page of Pearson correlation coefficient. Okay, and probably this will really give you an amazing idea with what we are actually solving. When I plotted this graph, you can see this. When I probably plotted this graph, it looks quite good, right? When x is increasing, y is decreasing. Sorry, if x is increasing, y is increasing. It is satisfying this condition. Obviously, we are definitely going to get a positive value. Now, I have opened the Wikipedia page. Let's go over here and see on the right hand side. This shows this suppose if I have this points that is plotted in this way, right? It is showing the correlation as -1. If I'm plotting this, see over here you'll be seeing x is decreasing, y is also decreasing, but it is still not in the straight line. So your value will be ranging between -1 to 0. Here you can see that when x is increasing, y is increasing, but it is not exactly in the straight line. So your value will be between 0 to 1. Similarly, in our case, here you can see that all the values are not in the straight line. It is something like this, right? Some points are here and here. So I'm actually getting 66%. So the value is between 0 to 1, right? It is positively correlated. Now here, if you have all the points in a straight line, definitely you'll be getting as +1. Now, if you don't have any correlation, that time your row, that is your coefficient correlation, will always be 0. Okay. So here also you can see some examples: 0.1, 0.84, 0.4, -0.4, -0.8. All these things you will be able to see over here, right? So I hope you have got an idea. Now, let me talk about one more example. This example is pretty much important. Let's take this example, okay? Now, in this example, you will be seeing that as x is increasing, y is increasing at every point, okay? At every point, you will be able to see that when x is increasing, y is increasing at every point. In this points, the growth, the increase is little bit slow, okay? Because the line looks something like this, right? The growth is, I mean, when the x is increasing, y is also increasing, but it is increasing by a smaller number, right? So in this case, we know that it is positively correlated. But even though we know positively correlated, when I try to find out the Pearson correlation, it is 0.88, right? It is 0.88. So even though it has a positive correlation, that basically means it is increasing. It is not decreasing somewhere. If it is decreasing somewhere, then I can say that, okay, the Pearson correlation will be a little bit less. So in this scenario also, I need to get the Pearson correlation as 1 because it is increasing. But that is not possible by the Pearson correlation formula. That is the specific reason why we are using Spearman correlation formula over here, right? Now, Spearman correlation, if I apply a Spearman correlation formula in this case also, where probably in this point also when x is increasing, y is increasing by a smaller amount, it is being able to capture this non-linear properties also. Understand, in Pearson correlation, which I probably showed you in this diagram, right? Over here you will be able to see that it only captures the linear properties, but every time it is either increasing, all the points are basically increasing. Okay, at some point it may be decreasing. So it captures the linear properties, but it fails to capture the non-linear properties. Understand, again I'm going to write it down over here. One basic disadvantage of Pearson correlation. Okay, so disadvantage of Pearson correlation: it is not able to capture the non-linear properties. Able to capture the non-linear properties, right? That basically means when the x is increasing, y is also increasing by a smaller amount, but it is not able to capture. So because of that, it is showing Pearson correlation little bit less, like 0.88. Okay. So in order to non-linear properties, okay. So in order to overcome this disadvantage, what we use? We use Spearman rank correlation coefficient, right? We use this, right? So if I probably take an example and show it to you, how does a Spearman rank correlation coefficient formula looks like, it is very much simple. Here it says covariance of rank of x comma covariance of rank of y divided by standard deviation of rank of x and standard deviation of rank of y. So let me write down the formula over here. Okay, so the next point, that the third point that I will probably be doing is Spearman rank. It focuses on rank correlation coefficient, right? And the formula is pretty much simple. Okay, so let me just see the symbol once again. It is given by R of S. Okay, so here R of S is nothing but, it says covariance of rank of X. Okay, covariance of rank of X. See guys, covariance of rank of X comma rank of Y divided by rank of standard deviation of X multiplied by rank of standard deviation of Y. See this, right? Or I can also write this as a little bit different. I'll write, okay, standard deviation of rank of X multiplied by standard deviation of rank of Y. Now you need to understand what is this rank. What exactly is this rank, right? We really need to understand. Let me take the same example. Okay, let me take the same example. And probably guys, I will probably give you one homework in this. Try to solve it. Okay, it will be fun. Economic growth by percentage. Okay, and then I have this Nifty 50 index growth. Okay, growth in percentage. Suppose I say 2.1 is this value, 2.5 is this value, 4.0 is this value, 3.6 is this value. Okay, and then I have 8, 12, 14, 10. Now this is my x, this is my x, this is my y. What is rank of x? Understand, what is rank of x? Over here I'll see which is basically given the highest rank. Obviously 4 is the highest value, so I will give this rank as 1. Then which is the second rank probably element? I will give 2.5, then third rank, then fourth rank. Similarly, if I try to find out the rank of y, what is rank of y? Which is the largest element over here? 14. So I'm again going to give this value as 1. Then probably which is the second element? I have this, right? So here I'm going to give it as 2. Here I'm going to give it as 3, and here I'm going to give it as 4. Now I'm going to take this rank values and then probably assign in this and try to find out the covariance and standard deviation and all. Now I'm not going to consider this two feature. I'm not going to consider this and this. Instead, my new data set will be this one. Okay. Now this is my new data set, and now I will go ahead and apply my Spearman rank correlation formula with this data. Okay, with this data. Now please go ahead and try to compute it, guys. Just try to apply the same formula and then try to see whether you will be getting 1 or not. Okay, my thing is that definitely you will be getting 1. I want to give you this as a homework. Please do it. And in this entire session we have in this entire session we have learned about covariance, we have learned about Pearson correlation coefficient, we have understood like what was the disadvantage in that, and then finally we understood Spearman rank correlation with some amazing good examples.